Hey everyone, so we're going to go ahead and give this a try. I decided it might be helpful for some people to have a little bit more to work with than just reading the book and answering questions. So I am going to start this YouTube channel to see if this will be helpful as we go through lecture notes like we normally would in class. I certainly miss seeing you guys and interacting with you guys, and I hope everybody is doing well and adjusting as best as we can to our new normal here. And I do hope that we get to see each other again soon. So before I go any further, please do let me know if this is helpful and let me know if you have any questions. So you can drop your comments in the comment box below, or you can shoot me an email and I will try to answer your question in the next video that I shoot for tomorrow. Ms. Warren has really slow internet, so I am uploading these videos as quickly as I can. The good news is that next week when you guys are on your spring break, I will go ahead and get everything lined up so that we are ready to go with our next unit when you come back. So if you can be patient with me through this little bit of a lag, I promise that I will get everything together for you and we will be good to go when we get back from spring break. One other note, we are going to try to have a test on Friday. I understand that there is a lot of newness being thrown at you guys. I understand that, you know, some of this is not as seamless as we all wish it would be. So nobody's going to fail because they couldn't figure out their technology, but I would like you guys to give your best effort because I really want to make sure that you guys are getting some grades that are not just answering questions out of a book. So if that sounds good to you guys, please help me out and let's try to do this thing. Okay, so we're going to talk about energy, which you guys have been reading about for the last couple of weeks. We're going to talk about energy, and we're going to talk about thermal energy, and then finally work and power. So I'm going to break this into two videos so that they're not so huge to upload, and we will go ahead and get started. So what is energy? Energy is the ability to cause change. We measure energy in joules. So in physics, we indicate that by the uppercase J. And 1 joule is equal to a kilogram times a meter squared per second squared. And that by itself doesn't really mean anything out of context. So for the purpose of this class, we're just going to focus on that energy is measured in joules. We're going to learn that there are many different types of energy. And again, you've already been reading about them for a couple of weeks. So we're going to start by learning about kinetic and potential energy. So kinetic energy is energy in motion. So we indicate kinetic energy by a uppercase K and an uppercase E. We calculate kinetic energy by taking 1/2 times mass times velocity squared. And again, this is a formula that I will give you on your test, so you do not have to memorize it. Okay, so it is very important for this formula that mass is always measured in kilograms. In a more advanced class, you might get a measurement that was given to you in grams. You would have to do a unit conversion. I will not make you do that for this test, but please do double check when you're looking at questions outside of the realms of this classroom, make sure that it is in kilograms. It's really important. Velocity, we know, is measured in meters per second. All right, so this is our first example. A jogger with a mass of 60 kilograms is moving at a speed of 3 meters per second. What is the jogger's kinetic energy? So what is the first thing that we always do when we're working these problems? We list out what we know and what we're looking for. So we are looking for the kinetic energy. We are given the mass, which is 60 kilograms. We are given the velocity, which is 3 meters per second. And we know that the formula for kinetic energy is 1/2 mv squared. So what we are looking for has already been isolated. The formula is all nice and neat. It's already written that way. So we're going to just go ahead and plug it in. So 1/2 of 60 times 3 squared. So we know from order of operations that we always want to get rid of the exponent first. So 3 squared is 9. And then on the other half of that equation, 1/2 of 60 is 30. We are left with 30 times 9, and that gives us Ke equals 270 joules. Alrighty, we have practice time here. I do not want you to try to mess with number 2 or number 3, because those are asking you to rearrange it, and that's more than we're going to do here. So I just want you to go ahead and focus on number 1. So go ahead and pause the video. Try to work that one on yourself on a separate sheet of paper, and then play the video, and I will give you the answer. All right. So the answer, the kinetic energy is equal to 120 joules. And I'm sorry that I have colored all over that and therefore made it difficult. So it is 120 joules. Okay. The next thing we're going to talk about is potential energy. So this gentleman who's standing here on the edge of the cliff here, even though he is not moving, he is storing energy. And so in fact, we refer to that as potential energy, energy that is stored by this person not moving. So it is stored energy. There are three types of potential energy. There's elastic potential energy, chemical potential energy, and gravitational potential energy. All right, we'll talk about them one at a time. So elastic potential energy, this refers to energy that is stored in objects that are being compressed or stretched. So compressed, of course, we're talking about something that is smushed in, and stretched, we are stretching it out. So I know that maybe a handful of you have possibly participated in archery. And so you know that when you draw back that bow, there's kind of a force that fights against you. And that is that elastic potential energy. It's energy that you were storing in that bow as you were drawing the arrow back and putting pressure on it. So bow and arrow. Another example would be a spring. If any of you have been lucky enough to play with a slinky, you know that when you push the slinky together, it has a tendency when you are no longer touching it to stretch back out. So that is because of the stored elastic potential energy that is in the slinky or in any other kind of spring. And finally, a slingshot. If you've used a slingshot before, hopefully not to shoot at your siblings, when you pull that slingshot back and then let go, that rock or that pebble or whatever your weapon of choice is pushed forward. That is because of the elastic potential energy that is stored in that slingshot. Okay. Potential energy in the form of chemical potential energy. We are talking about the energy stored in chemical bonds of compounds. In the first half of the year during our study of chemistry, we talked about different kinds of bonds and about how energy is stored in those bonds. So an example, a practical example of chemical potential energy would be in a battery. The way that a battery works is there is actually chemical energy stored in it. When you put that into your device, that device converts that chemical energy into electrical energy to, say, power on your flashlight or to use your TV remote or your gaming system remote. So that would be an example of chemical potential energy that is stored in that battery. Fire is another example of chemical potential energy. We learned earlier this year that combustion, or the setting something on fire, is actually a chemical reaction. And then finally over here, this picture of a banana that's partially skewed by my speaking box over here is food. So we learned last year that the energy from your body comes from breaking down the food that we eat, and that is because there is chemical energy stored in that food. Our body breaks that food down, it releases that energy in the bonds, and then that's the energy that we use to move our muscles and to perform all of the other processes that require energy in our body, like cellular respiration and all that stuff. All right, and now we'll talk about gravitational potential energy. This is abbreviated GPE, and this is referring to energy stored in objects that are above Earth's surface. I hesitate a little bit to give you this formula because I don't want you to feel that you have to memorize it. I am not going to give you any mathematical problems that have to do with potential energy. The reason that I am putting the equation here is because I think seeing it helps us understand really what gravitational potential energy is talking about. So the formula for gravitational potential energy is GPE, which is the abbreviation for gravitational potential energy, is equal to ham. Height measured in meters, acceleration due to gravity measured in meters per second squared, and mass measured in kilograms. Now we know that acceleration due to gravity is always going to be the same number. It is always going to be 9.8 meters per second squared. So if this A is always going to be the same value, we know that either increasing the height or increasing the mass is going to give us a greater gravitational potential energy. So if we really take a moment and think about that, it really makes sense. If you had two items that had the same mass, so let's say you had two rocks or two books, and one person climbed up a 10-foot ladder and dropped the book, and another person climbed up a 20-foot ladder and dropped the same book with the same mass, we know that if something is further up and is dropped, it has a greater force when it hits the ground. And the reason for that is because it has a greater gravitational potential energy. Similarly, if two people climbed up to the same height, so if height was the same for both, but one person had a book that weighed 10 pounds and one person had a book weighed 50 pounds, we know that when the 50-pound book hit, goodness forbid if there was something beneath it, it's going to hit with a greater force than the lighter book. So if they are at the same height and one is heavier than the other, the heavier one is going to have a greater gravitational potential energy. If they are the same weight and one is higher than the other, the higher one is going to have a greater gravitational potential energy. So I do not want you to worry about having to do a math calculation with this formula, but I do want to use it as a tool to kind of understand what we're trying to say here, that things that are heavier or higher up are going to have a greater gravitational potential energy. Okay, so now moving on to the law of conservation of energy. And so you'll see kind of a theme as we move through physics that there are a lot of laws that are the conservation of matter, the conservation of energy. There's a lot of conservation laws. So the law of conservation of energy is that energy can never be created or destroyed. It can only change forms. Because of this, it is important to understand all of the different forms that energy can take. And so we've already covered a few. We've talked about gravitational energy. We've talked about chemical energy. We've talked about, well, I just drew a blank. Anyway, we're going to learn about some other forms of energy. All right, so the first one is radiant energy. So really radiant energy is anything that generates light. So light that comes from the sun or light that comes from a light bulb. We use it to see and as a power source. And radiant energy is also very closely related to thermal energy. Radiant energy is also referred to solar energy or light energy, but that's kind of given. And so the reason that radiant energy is related to thermal energy is many of the same things that generate light also generate heat in the process. So if you think about it, if you light a light bulb and then after it's been on for an hour you touch it, it's probably not going to feel very good because it's probably going to be very hot. Similarly, we know that the light from the sun is how we can see when we're out and about during the day, but we know that that sunlight is going to be reflecting heat. So both of those generate light and heat. Similarly, fire. We know that if we're around a campfire in the evening, in addition to being warm and cozy, it also allows some light for us to see. So radiant energy and thermal energy are very closely related. Okay. Electrical energy. This one seems pretty straightforward. This is anything that comes from outlets and power plants used to power electrical devices. So if you have something that plugs into the wall, it is using electrical energy. Sound is also a form of energy. We are going to talk more about electrical energy in our next unit, and then our final unit will be about waves. And so we're going to talk a lot more about energy in the form of electricity and sound, but for right now, we're just going to recognize them as forms of energy. And so sound comes from a variety of sources, and it's used most often for communication. So the sound coming from your phone, the sound coming from your computer speaker right now as I'm speaking, the sound coming from a megaphone that maybe Coach Barb has in the gym. All of these are actually forms of energy that are traveling from the source of the sound to your ear. And then we have nuclear energy. We did already have a unit over nuclear energy and how nuclear power plants break down atoms, and that energy that comes from the nucleus of those atoms is what's used in a nuclear power plant. Now, electromagnetic, this is to me the most fascinating form of energy because it's kind of what all of the new cool technology comes from. It's the form of energy that is reflected or emitted in the form of electrical and magnetic waves that can travel through space. So the Snapchat that you send your friends, that is thanks to electromagnetic energy. When you get in your car and you turn on the radio, the fact that you can just have music on demand, that is thanks to electromagnetic energy. Cable channels, when you turn on the TV and you have 156 channels to choose from, that is thanks to electromagnetic energy. And so that is a very sophisticated combination of electric and magnetic waves. We'll talk a little bit more about it when we talk about waves and electricity, but really, really cool, fascinating stuff. Okay, so often we have energy transfers. And so as we're moving through this, I want you to kind of start thinking about being able to identify these energy transfers. So this first picture here, these are fireworks. And so what do we have to do to a firework to get it to light? We have to ignite it. And as we talked about before, there is a relationship between heat and combustion and light. So in this first example, combustion is a chemical reaction. It is causing, when something is burning, it causes radiant energy and heat energy. But in this case, it is going to light, thermal, and sound. So we know that when a firework goes off, it creates a large sound. So this is an energy transfer where we started with chemical energy and it is turned into light, thermal, and sound energy. What about these solar panels over here? What are we doing here? Well, we are starting with energy from the sun, so solar energy, and we're turning it into something that is useful to us, which is electrical energy. In this example in the bottom, we are taking electrical energy, we are plugging this string of lights into the wall, and we are turning that energy into light. So we're going from the electrical energy to light energy. In this example here, we are plugging our phone in to charge it. And from our phone, we get light and sound. And so this is an example of electrical energy being changed into electromagnetic energy in the form of, and additionally light and sound. So this, hopefully you can do me proud and remember from last year our extensive conversations about photosynthesis. And so photosynthesis, we start with light and we are able to turn it into chemical energy. We are dependent on the plant's ability to do photosynthesis because we rely on that as our form of being able to get that energy from the sun ourselves. So plants harness that solar energy, they turn it into chemical energy. We eat that food in the form of plants, and then we are also benefiting from that chemical energy because of course we as animals cannot get that energy directly from the sun. And so we are very dependent on photosynthesis. So that is a really important energy transfer. And then finally down here, this is kind of a little bit more of a thinking outside of the box energy transfer. But this gentleman here is playing the guitar. And so he is moving his fingers, and that is kinetic energy. And he is transferring that kinetic energy into sound because this guitar is making a sound, and the sound will eventually reach our ears. So that is an example of kinetic energy to sound. On this last slide, I just want you to focus on the definition of mechanical energy. So mechanical energy is the total amount of kinetic and potential energy in a system. And so really, we're just going to stop there at that definition. We are going to talk, you guys have already read and answered book questions on simple machines and how mechanical energy relates to them. We will talk a little bit more about work and power in the next lecture. But right now, I just want you to have this definition and just kind of put it off to the side and hold it, and we will come back to this concept. So that is as far as we're going to go on this first section of lecture. Please drop a comment or drop me an email. Let me know if this was helpful. Let me know what questions that you have, and I will try to address those questions in the next video. I am going to try to well, actually, let's see. They won't be answered in the next video because I'm going to try to get both of these videos posted so that you have them to take your notes from. But do email me with questions and I will email you back answers. And then in the following video, kind of a follow-up video that I'll post later this week, I will answer those questions in case somebody else in the class had them. So it was great to virtually be with you all for just a few minutes, and I will talk to you soon. Bye.